Machine learning becomes increasingly adopted in clinic, it will continue to reduce costs, increase patient throughput, and improve patient outcomes. An effective model needs to incorporate the information from new data into its parameters, since patient populations change and the definition of disease changes as well. However, updating models naively can present serious risks. Consider the following example. A clinician is deciding whether to continue or stop treating a patient in the ICU. If the clinician thinks that the patient has a high chance of living if treated, then they receive treatment. Otherwise, they will not receive treatment. Now consider a machine learning model that predicts if someone will live or die. A false positive here means that the patient could have lived if they were given treatment, yet the model predicted death, so they were not given treatment and ended up dying because of that. We refer to a feedback loop as when a model can influence future labels through its predictions, and if it is updated using those corrupted labels, its bias is reinforced. This cycle repeats as it is updated more often. The effect of feedback loops can be significant, as is seen here on Mimic 4 data, where we are performing a binary mortality prediction task. We have three random forest models, all of which were initially trained on data from 1996 to 1997. The static model, or green line, is never updated. The no feedback loop model, or blue line, assumes that the clinician does not know about the predictions of the model, so the model is updated using clinician predictions only, which we consider to be the ground truth labels. The feedback loop model is updated using the model's correct as well as incorrect predictions. As is observed, it is best to not update the model when its predictions can influence future labels. If a clinician uses the model's predictions only some percentage of the time, and that percentage depends on the model's performance, then the effect of feedback loops can be slowed down. This is shown here by the orange line having a lower false positive rate than the blue line. Although false positive predictions from the clinician can also affect the labels of future update samples, these false positives are independent from those of the model, so there is no reinforcement of bias. Here we look at the performance of an XGBoost model with various regularization schemes. On this plot, higher is better, whereas on the previous plot, higher was worse. Dropping all positively predicted samples, the green line, is nearly as good as dropping all samples that were mislabeled by the model according to an oracle, the blue line. More clever schemes were also investigated, yet were not effective due to poor model calibration, which is in part a factor of the class imbalance in the data as well as the difficulty of the prediction problem. In summary, we investigated the feedback loop problem, which has been mentioned by researchers in the past but never been examined. This is a difficult problem to solve, especially when the underlying data distribution changes. Having a model with an auxiliary output that is able to defer prediction to a clinician is an interesting future direction. The goal of this work is not to discourage the use of machine learning models in clinic, rather to raise awareness of what can happen when they are able to influence future data that is later used for updates.